All right, howdy everyone. We'll get started. So welcome to today's review session. This will be the last one, and thank you for being flexible today. Just had a couple conflict things happening between work and life. So thank you for being accommodating. This is being recorded, so if you need to look back at it afterwards, you're more than welcome to do that. I'll just post it under my office hours link on the first resource page once I get that recording back. And then as a reminder, your final is tomorrow at 10:30 a.m. and just in the same room that we take lecture in. So no need to worry about like finding a new place. It's just right in that ILCB 113. And if you need anything from me after this review session is done, I'll be on top of my emails as much as possible. So just send me an email if you have any additional questions after this. All right, so the next hour is yours. You can ask any questions that you would like. You can use the chat or take yourself off mute. And I have the practice exam pulled up in case you want to look at the mock exam. But if you just want to do a general content review, you can also ask for that as well. So I am open to anything if anyone has any suggestions or questions that you would like to go over today. Anything specific that we want to see? Yeah, absolutely. So when we look at orbitals or just like quantum numbers in general, our N, L, M sub L, and M sub S all have different rules. So our N tells us our energy level. Right, so the higher the number, the higher the energy level. So you can have 1, 2, 3, 4, 5, 6, 7, technically in terms of the N level that you can have. Right, so once we know our energy level, and then L has the rule of N minus 1, right? So you can have, if N is equal to 2, then L can equal to 1 or 0, right? Those are your two options you have if N is equal to 2. This tells you your shape of your orbital that you're in. So this would be 0 is equal to S, 1 is equal to P, 2 is equal to D, 3 is equal to F, right? So you can have S, P, D, or F, and that's corresponding to 0, 1, 2, or 3. And then for M sub L, this tells you your orbital, right? Or the area in which that you are in. So your SPDF is your subshell, your M sub L is your orbital. I think I'm saying that correctly. Maybe just double check that to make sure that that's correct. But this can be negative L to L. So as an example, if L is equal to 2, then M sub L can equal negative 2, negative 1, 0, 1, or 2. Okay. Then M sub S, this is just your spin of the electron. And that's going to be plus or minus 1/2, right? You can either have an upspin plus 1/2 or downspin, which is minus 1/2. When we look at, I'll just clarify this so I don't think. Yeah, okay. So this is your, this is your subshell, and this is your orbital. And what is important to note here is that you have the s orbital only has one subshell. And that's like when we draw our pictures, right? We only have one box for the S subshell, right? This is 1s2, or 1s, right? That's the box for 1s. Where your p orbital has 3 subshells, and that's why we draw a box with 3 boxes, and this is, right, your 2p. That was something that we draw between that. So in your s orbital, you have 1 subshell. In your p orbital, you have 3 subshells. In your d orbital, you have 5 subshells. And in your f orbital, you have 7. Then each subshell can hold 2 electrons. Okay. Any questions on orbitals, or does that answer my orbital question? Subshells are m sub l.
Can I ask a question?
Yep.
I orbitals have higher energy than the p orbitals. Is that correct? Like if
Say
we're
that
thinking
one
about.
Say that one more time. Sorry.
Oh, let me get inside. Sorry, I'm walking. But the d orbitals, don't they have like, if your n is a higher number, doesn't that mean you have like more energy in your orbitals?
Yes. So the higher level the n is, or the higher the number of n is, the higher the energy is. So like n is equal to 3 is greater than n is equal to 1. So a 3D would be greater than a 2D orbital. Wait, let me rewrite. Let me just do that. 4D is greater than 3D.
So does that imply that a 4s orbital will be greater than a 3d orbital?
That depends on the building up principle. Right. So that's when we look at, right, we look at our periodic table. Right, this is hydrogen here, this is helium here. Right, so this is 1s, this is 2s, this is 2p, this is 3s, this is 3p, this is 4s, this is 3d here, and then this is 4p. So your 4s here is lower in energy than your 3d because you build in high or low energy to high energy. So 4s comes first, going left to right. So therefore you fill in the lowest energy first, which is your 4s, and then your 3d.
So if we wanted to like make, because I know there's like the ground state and excited state for electrons, like whenever we do configurations.
Yep.
If we're dealing with one of those transition metals, if we wanted an excited state, does that mean we take from our 4s and put it in our 3d?
Yeah, you can do that as an option. Any sort of like ground to excited state is just taking an electron from any place and making it higher. So if you have something that is 4s2 3d3, you can either make this, right, this is ground state. An option could be as an excited state 4s1 3d4, or it could be 4s2 3d2 4p1, right? As long as you take one electron and put it into a higher energy level, then that's considered an excited state.
A ground state, that's just like your base form. So like if I want to make something like a ground, like am I able to put a energy or am I able to put an electron from a higher energy orbital to a lower one? Or no? Is there like
No, that's not an excited state. A ground
is
state
it,
is the least energy possible. So you can't
oh, okay.
if you have, we have like copper is 4s1 3d5. That's its ground state electron configuration because it's more stable to have the s orbital unoccupied. And then right, it would look like this.
Because that's one of like the exceptions, correct?
This is one of the exceptions. Yep.
It's
Right. So it's
copper and
easier.
chromium.
Yep. It's easier and more stable for the copper or chromium first. I think this is chromium. Yeah, sorry, this is chromium. right? Chromium is 4s1,3d5, so it's more stable for the electrons to be unpaired than it is to have one paired in the 4s. So you can't say an excited state, you never put it down, right? You would never say that this would be 4s2, 3d4. It would,
Okay.
that wouldn't be an excited state.
All right. Okay.
It
I
would
think I
always,
understand.
yeah, it would always be probably like this. This would be an excited state.
All right. I got it. Thank you.
Yep. Yes, this is the ground state for chromium. Yep, so the two that you really are responsible for are chromium for an unusual, and then copper is 4s1, 3d10. So that looks like that.
So I guess just in summary, I'm always taking from, if I'm excited, I'm never going into my 4s. I'm going into 3D.
Okay, I can say.
Like just for transition metal.
Yeah. I mean, like you don't really want, if you're going to make it a transition metal excited, take an S and put it in a D instead of taking a D and putting it in an S.
All right, got it.
Or take a D and put it in a P. Like just go up, go to the next one, go something to the right. Okay, any other questions on orbitals, excited state, ground state? Does that answer our questions there from the couple that came through? Okay, so for Cl2 minus, for Cl2 minus, for this Lewis structure, chromium, chlorine has 7 electrons times 2. So we have ICl2. Chlorine has 7 electrons times 2. That's 14 from chlorine. I has 7 electrons times 1. That's 7 from iodine. For a total of 21. We have this minus, so that's going to be plus 1. So we have 22 total electrons. If something is by itself, that's usually going to go into the center, and then the least electronegative is going in the center. So iodine is going to be center. And we have 2 bonds of chlorine going out to either side. Those are going to take 2 electrons each. So that's 4 electrons that we're using. So we have 18 left over. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We fill the octet of our outside ions. And then we have 6 left over. So we're going to do 1, 2, 3, 4, 5, 6. So that will have 3 total lone pairs on the iodine. And iodine can have more than 4 electron domains because it is lower than energy 3, or the n equals 3 sub energy level, right? It's an n equals 5. Yeah, it's an n equals 5. So it's able to expand its octet because it has that extra d orbital in there. And we do want to minimize charges on the central atom. However, since we have this charge associated with our compound, we need to have some sort of charge associated with the atom as well. So if we solve for the formal charge of our atoms, we look at chlorine, or we'll say formal charge first, is your valence electrons minus the lines plus the dots. This is bonding electrons and non-bonding electrons, right? But you just do lines and dots, that gets into your answer. And if you look at the formal charge of chlorine, then we know that chlorine has 7 valence electrons. It has 1 line and 6 dots. So it has a formal charge of 0. However, if we look at the formal charge of iodine, then we again have 7 valence electrons. This time we have 2 lines and 6 dots. So you have a formal charge of -1. It is allowed to have a -1 charge because the overall atom or the overall molecule has a -1 charge. So this is 0, 0, -1. That's okay because it's in the center, and we need to have some sort of -1 charge, or all of our formal charges need to add up to that overall charge of our molecule that we're looking at. So that's an okay why that one has a charge on the central atom.
May I ask a question?
1 second. So if the initial charge is -1, like in this case, right, this one ICl2 minus has a -1. You want to aim for as many as your electron, or as many atoms to have a formal charge of 0, but one of them at the very end has to add up to -1. So if this was something where it was, right, if this looks like, say, -1, -1, +1, right, that would be a bad Lewis structure because we have too many that have a charge associated with it. Even though it is adding up to -1, we want to minimize formal charge as much as possible. And as much as possible is the key term here, because we want it so that 2 atoms have 0, 1 has -1, giving us the charge that matches our charge from our initial compound. Does that make sense, Seth? Great. Yep. And then I would say you would need to know your 3 exceptions for the Lewis dot structures. Right. So that's beryllium just has 2, boron has 3, and then above n equals 3 can expand its octet. I think those are the big ones. And then, right, hydrogen only wants 1. Helium wants 2. Okay, you can ask your question now, Matthew.
Yes, just to make sure when drawing the formal charges, your electrons at the end, so your central, or I guess just when focusing on the end, so in this example, the chlorines, like, are we supposed to be more positively or negatively charged? Because I feel like I remember there's a rule about that.
The more electronegative, the more it should be, the more electronegative can hold on to the charge more, because it wants that electron more. But in this case, we'd rather have the more but in some cases you want the more electronegative atom to have 0. And right, and this would minimize charge. If you did this where, like, chlorine cannot expand its octet, so you can't take one of these electrons and put it here to make you can't make this, because then this gives 5 electron domains to chlorine, and chlorine can't expand its octet.
Okay, and also your most electronegative in most cases is your central atom. Is that correct?
Your
Okay.
most electronegative is on the outside. Your least electronegative is on the inside.
Least is on the inside. Oh, okay, okay. And you want your most electronegative to be closer to 0?
You want your most electronegative to be closer to 0. Yes.
Okay, I understand. Thank you.
Now that I'm thinking about this, chlorine can expand its octet, but we can't make 5 bonds. You don't want it to make 5 bonds. So this just looks ugly. This is ugly. Don't do this. This is the nicer one. This is your structure.
So can your central atom have a positive charge? Like, is that allowed?
Yeah, absolutely. Yep, you can definitely have a positive charge.
But and you could have negative and positive, so it doesn't. All right.
Okay. Um, are we gonna have to ID principles? I would be familiar with them. I do remember having him giving a question. I think it was on exam 1 or 2. Um, just asking like which rule is not being followed. Um, I would say just like kind of brief up on those a little bit. Maybe know like what the Aufbau principle is or know what the Pauli exclusion principle is. That way, if you see one of those and then like a different principle comes up, you're like, oh, it's not these two that I know, kind of thing. If you don't know them, it's fine. But I would just briefly look at them before you come in so that you just know the difference or you recognize the names. Yes, formal charts is dots and counted by lone pairs. Yep. So like when you're looking at chlorine, in this case, you're counting like if you split this bond in half, right? Because you want half the bonding electrons. So then you have 1, 2, 3, 4, 5, 6, 7. I guess I should. Right, you have 1, 2, 3, 4, 5, 6, 7. 7 from these. Half of the bonding, which is 1/2 times 2, 1, and then you have 6 dots or 6 lone pairs. 3 lone pairs is 2 electrons, so that's 6 electrons there. Is the final going to be mostly focused on material after exam 2, or will it be more cumulative? I would say that it's going to be 50% new material, 25 old from exam 1, 25 old from exam 2. That would be my guess. Maybe like 60, 50, 60 new stuff split between the other. But you know, everything builds on each other, so it is a fairly cumulative exam. I would say that the newer material, right? So what sections should you focus on more for the final? I would make sure you're pretty solid with the new material just because that will be the majority of the exam. But you'll probably have to do a percent calculation or percent mass calculation or percent abundance kind of thing. Looking at stoichiometry and all that stuff. So stuff from the beginning of the semester as well. Waves and light and electromagnetic spectrum. Yes, yes, use 63 for this one. Yeah. He rounds it a bit. But when you get this answer, I think you get like 69% and 31%, and the closest is this guy. So on a multiple choice test, I would say use that one.
For that question, it says the correct answer was C for 16.
Oh, did I read that question wrong? Yes, sorry. Hold on, let me look at my answer key. Yes, sorry. So when you use it with the periodic table number, then you get like 69, whatever, 75%, but it is going to be 90, and you want to use the 63 for this. It will be obvious on your final what mass you should use. So as long as if you got B or C, then you're doing it correctly.
So are we using is this the mass for like the one we're equating to, or are we using the mass from the periodic table?
What do you,
Like, the way to solve this is you create like a system of equations where you have like your masses times your percent abundance, and that should equal your average, which is on the periodic table.
yep,
So are you saying for the weights that we're given, we use 63 and 65 as our given masses?
I believe so. I
That
mean, if you did this, if you got B or C, you're doing it right. It will be very obvious to you on your final which one you should do. Just keep doing that same math. So if you
okay,
got B or C, don't be worried. You did it correctly. You're fine.
got it.
Yep. Um, so for diatomic molecules, just make sure I would know those. And then I would know just like your strong acids, strong bases, maybe just recognize those. Um, there's 6 strong, 6 weak, and or so 6 strong acids, 6 strong bases. I would say just knows those. And other than that, I think anything else that you would need would be given to you either on your solubility chart, your formula sheet, or like your conversion charts.
Um,
Yeah, yep. Sorry, go ahead. Who's ever talking?
could you give us like a rundown on like identifying polar molecules versus non-polar molecules?
Yep. So that plays into Emily's question as well. So when you're looking at electron domains, where you're looking at Lewis structures of atoms, I would say I could probably do the math actually. I would say like 95% of the time, if you have a lone pair, the molecule is polar. However, there are 2 exceptions. That is when you have 5 electron domains. If you have your central atom X and I guess your central atom M, and you have this shape here, which is linear, your X's are axial and your lone pairs are equatorial. And the lone pairs being equatorial and the X's being axial will cancel each other out, and therefore this would be a non-polar molecule with polar or with lone pairs. Okay, so that's one exception. The other one is 6 electron domains. And if you have this one, you'll have 2 lone pairs and you'll have 4 bonding 4 bonding atoms. This one is square planar. And this time X is equatorial. And your lone pairs are axial. Your lone pairs being axial will cancel each other out. And then your equatorial atoms are in a square. So they're pulling at like the corners if you do the diagonals. And those will cancel each other out as well. So as long as all of your atoms are the same and you're have 2 lone pairs for the square planar or 3 lone pairs for the linear, then this will be non-polar with lone pairs. any other time you see lone pairs, it will be a polar molecule. So something like water, right, that has lone pairs. This is a tetrahedral electron domain, and that it is a bent molecular geometry. And so this is a polar molecule. Does that help a little bit with polar molecules? And
Yes, thank you.
yep. Right, so then you just need to remember your other shapes. So I guess going to diatomic molecules, right? If you know your shapes, that's like the big thing. Right, you have tetrahedral, trigonal bipyramidal, you have your octahedral, those are the big ones, square or trigonal planar, that's right, big three, big four, and then everything underneath it. Square pyramidal, seesaw, bent, T-shape, all that fun stuff there. So just make sure you are remembering those as well. Okay. Just make sure. Okay, so then we look at vapor pressure. This is looking at boiling point. And the vapor pressure is if you have a cup, say, and you have water, and this is lidded. Right, the vapor pressure is the pressure the gas molecules are making on the container above the water. So if something has a strong IMF or high IMFs, this is going to equal a low vapor pressure, which means we have a high boiling point. Because if something is able to escape into the gaseous phase easily and create this vapor pressure, then that means that their IMFs are not held together strongly, right? Maybe they're just out here and they can pull apart really fast. But if you have something that is interlocked, it's a little bit harder for me to pull my hands apart before I can break them, and I have to overcome a lot of energy. So I'm not going to release or go into the gaseous phase as easily because I have stronger IMFs. If I'm not escaping to the gaseous phase as easily, that means I need to put a lot more energy into my system before it reaches that gaseous phase or it reaches that boiling point. So lower the vapor pressure, higher the boiling point, and vice versa, right? Higher the vapor pressure, lower the boiling point. And then that means if you have low vapor pressure, you have high IMFs, or like a high molecular weight as well. Those are more theory. Yeah, you might be seeing something that says like, you know, the vapor pressure of this gas is X, blah, blah, blah. And you could do some equations or some math there. But if we're doing that, it's more of mole fraction, where you have like P total is equal to the pressure of A plus the pressure of B. And those are partial pressures of A and partial pressures of B. So if you're given vapor pressure of those gases, you can look for the total for the total pressure. And then we know that the moles of A over the moles of total is equal to the mole fraction, or the partial pressure of A over the pressure total. So you can either have theory questions or something along the lines of these two equations here. What else? Yep, so for enthalpy and entropy, right, delta H, this is your enthalpy. And for delta S, this is your entropy. I think the big things that you're looking for when it comes to the questions here and what's related for your formula sheet is that this is going to be, right, your heat of reaction is going to be the sum of products minus the sum of reactants. Okay. And then we can also have one where your bond enthalpies. This one is your sum of your reactants minus the sum of your products. We talked a little bit about that in the last review video as well. If you're given tables where it's like, if we're given CO2, we're given carbon, we're given oxygen. I guess you would be given that. You're given H2O, you're given H3, you're given H2. Right, stuff like this, right? Anything like that. If you're given these molecules in delta H, then these were all going to be like negative 100, 1,000, negative 300, 298, 0, 0. Right. Maybe given actual values, this is your heat of reaction, looking for products minus reactants. If you're given something where you have carbon dioxide, and you have carbon oxygen, or you have carbon hydrogen, or you have carbon carbon, carbon carbon, or carbon carbon, right? These are now all bond enthalpies. We're looking at the energy right? These are all bond enthalpies, or the energy required to break this bond. And this is enthalpies of formation. Or energy required to make the compound. So if we're looking at the stuff on the left in that chart, we're looking at forming the actual molecule. If we're looking at the stuff on the right and the bond enthalpies, we're looking at what it takes to chop up those bonds or the energy that's released when those bonds are formed. So you need to look for keywords like what's the heat of reaction or what's the heat of formation for the equation on the left, or you're looking at what is the bond enthalpy or how much energy is required to form this bond, right? When they actually say the word bond, then you're looking for bond enthalpies, and that's going to be reactants minus products. Because it's bonds broken minus bonds formed. Okay, that's delta H. And then delta S is entropy, and that's going to be the same thing as the products minus some of the reactants. Okay, and all of that ties into delta G naught is equal to delta H minus T delta S.
For the bond entropies, whenever bonds are broken or formed, do we just use the number we're given, or do you have to like change the signs around?
No, for bond enthalpies, you can use it directly as is. You just have to count the number of bonds of that type that are being broken or formed.
Okay, I understand.
The number of moles of a reaction will affect both. So if you have a coefficient of 2 or 3, then you need to multiply that compound by 2 or 3 in both of those cases, in both enthalpy and entropy. Any other questions on whoever asked about enthalpy and entropy? Yep, perfect. Okay. Is there a question that does Hess's law on the mock exam? Feel like yes. So we talked about bond enthalpies last Wednesday. So in the most recent review session, if you want to look at that question again. Yeah, okay, so we'll do 8. So we're going to consider the following process and we're given delta H for the 3 steps in the reaction, and we're looking for B goes to E plus 2C. So the first thing you want to look at is that B is right. I always go left to right in my overall reaction. So for B, I see that the only time I see B in a reaction is in the first one or in the second one, right? So I don't really know, right? I have to manipulate those to which side it has to be. I have 3 of my, right? And so if I see that twice, I kind of move on and think, what else can I do instead? For E, I only see E on my left-hand side here. So in this equation, I can't do anything to manipulate it because E is on the right-hand side and it's, or is on the left-hand side and it's by itself. But in my overall equation, it's on the right-hand side. So since E only appears in one equation, I have to manipulate this one or that third equation in order to make it match the overall equation. So I'm going to flip this first guy. So that means that I get D goes to E plus A. And now my delta H is equal to negative 350, because if it is endothermic going from left to right, when I flip it, it is exothermic going from left to right. Now that I'm looking at that, I see that my next one is 2C. So 2C only appears in my first equation, and it's on the same side. So I have to keep this guy because 2C can be manipulated. It looks like how it should in the overall equation. It only appears in one equation, so I'm going to bring that down and say that 3B goes to 2C plus D, and my delta H is equal to negative 125. So now I have to look at what I have left, which is B. I need to get rid of A in my equation for like the new third equation. And I have 3B, but I need to get down to just 1B. So if I multiply this one by 2, then that gets me to A goes to 2B. And when I add all of those 3 equations together, the D cancels out, A will cancel out, and then I have 3B here and 2B here. So that will subtract, right? Think of the arrow as an equal sign. So that will just remain 1B on this side, forming E and 2C. If that matches this guy here, then you can add your delta H's. So then you get, I think 175. Then you get minus 175, which would be any questions there? Emily, can you be more specific with your question? I believe the final is pretty comparable to exam 1 and 2 in terms of the average. I think people tend to do better on exam 1 than they do on exam 2. So the average goes down a little bit for exam 2. And the final is kind of in between or closer to exam 1. I think the final practice exam is fairly reflective of the final. I haven't seen the final, but working with Dr. Bengali before, I think I know what he's going to ask. And so I would say that this is a very good representation of the types of questions you would see or the type of content that you would see for the final. And I do believe the syllabus was changed so that the final replaces the lowest exam. So if you have a reaction with more moles on the product side, then entropy will increase. But enthalpy stays the same, right? If you're looking at the number of moles for enthalpy, that doesn't matter in terms of like predicting if it's going to be endo or exothermic. However, if you only have, like if you have something where it's 3 H2 plus N2 goes to 2 NH3, and then this is delta H is equal to, I don't know, minus 100. Then if you say that you only have 1 mole you only have 1 mole of H2, then you have only 1/3 of that energy because the molar ratio is similar to the delta H. So you would say, okay, I have 1 mole of H2. So then for every 3 moles of H2, I have 100 kilojoules of energy, right? So then I'm only putting in minus 33.3 kilojoules, right? That's the energy, and that's how the moles work for that one. I don't know the total. I don't remember the exact replacement. I think it's the average of the two. I don't remember. I don't want to tell you the wrong thing. He might have put in an updated syllabus. I can ask him after this and just send him an email to see what he decided to do. Because I don't remember entirely what the difference was.
May I ask a question?
Yep.
So I redid all my exams and quizzes in preparation, and I don't recall ever seeing a question relating to acids and bases. I know we covered it earlier, but like, just what's the main idea for that concept? Like that you think we need to know?
I would just look at like titrations for that. So if you like, right, if you have something where it's HCl and NaOH, right, then you have H2O and NaCl. So if you have something where you're trying to, if you're trying to find the equivalence point, right, then you have like 1 molar of this and 0.5 liters here, and you have, right, 0.75 molar, then like what is the how much volume of NaOH do you need? So right, that would be the type of thing there where you're pretty much just using M1V1 is equal to M2V2 to find the equivalence point. Right, you would just need to do that, right? M1V1 equals M2V2. But remember that this is a like molar ratio. So if you have something that's H2SO4 and NaOH, right, then you're going to have H2, H2O, and Na2SO4. So then you have a 2-to-1 molar ratio. So then your M1V1 looks a little different. So that would be what I would say from acids and bases.
So am I just making sure? Well, because we're already given molarity in liters, so how would the coefficients affect it?
Because so if you're solving for like this one here, then for every 1 mole of H2SO4, you need 2 moles of NaOH. So if you're trying to get to equal moles, that's where that comes into play, right? So you would take 1 times 5 liters to get to 0.5 moles. So then you would say 0.5 moles of H2SO4 and 1 mole of H2SO4 is equal to 2 moles of NaOH. So then that gets 1 mole of NaOH. And then you can plug that into with your molarity and use it there to find the volume. So that's how like coefficients come into play.
That's if we're adding a certain amount of moles. Like
Say it again.
that's kind of like if we're adding moles, like we're saying we have this many moles of this and that. That's how they I guess.
This would be a titration. So like if you're looking to find the volume for the equivalence point, right? You're trying to find equal moles at the titration or the equivalence point. So so that's what you're looking for there, trying to find equal moles.
So that's just what equivalence point means?
Equivalence point is when the moles of acid is equal to the moles of base. Yes.
Okay.
But that's like, I would say that if you don't know acids and bases, then I wouldn't worry about it. Unless this makes sense to you now, because we just covered that at the very end, so it won't be a lot of stuff.
Okay.
Okay. I think someone asked about equilibrium earlier, and right, equilibrium is products over reactants. Right, so then you're just looking, and this is only for gas and aqueous. Can only go into K. So that's that's equilibrium. And then right, this plays into ice tables for like how you solve for K. And so KEQ, right, is right, K is going to be something like, if you're looking at an acid, we'll say H plus times right, it can look something like this, right, first, whatever. So those are, K is always products over reactants and then ice tables. Okay, I think someone asked a couple questions. Someone said, so if you say that if we do good on the practice exam for the final, we should also do on the actual final. I will never guarantee that, because when you take the final or when you take the practice final, you're not in a testing setting and you have your notes and resources available to you. And so in your actual exam, you might get a little bit more stressed. It might be a time crunch kind of thing. So if you did well on the practice final, I would say that there is a good chance that for you to do well on the final exam, but I will not guarantee any outcomes. Yes, so when we look at 15, right, this plays into equilibrium. So if we are increasing the temperature for this is delta H. So if we increase the temperature and it's a positive, where delta H is acting as a reactant here. And then if we increase temperature, we're increasing products, right? So I'll write that here and going towards reactants. So we're shifting equilibrium to the right. So this would not shift it to the right. Decreasing temperature though, we're now decreasing on this side. So we have to fill in that void. So this would increase, that would shift the equilibrium to the right. Increasing volume, we're looking at number of moles of gaseous products and reactants. We have 4 moles and then we have 2 moles. So if you're increasing volume, then you want to go towards the side with more volume, with more moles. So this would increase here. We would go that way. So that increases to the left. However, decreasing volume, you want to go to the thing with less moles. So it's going to decrease on this side, making sure that we shift to the right. So this would shift to the right. If we remove some NH3, we're taking some product out of our solution or out of our reaction. So then we're going to shift to the right to fill the loss of product that we had. So that will shift it to the right. If we add some NH3, now we're increasing our products. So now we're shifting to the left because we have now like a mountain, right? Consider we have a mountain here. And so we need to fill and go to the left in order to shift that mountain all over. So this will go to the left. If we remove some N2, right, we're removing on the left-hand side. So we'll refill that valley that we created to create more reactant. And then if we're adding some N2, then we're increasing our reactant side, right, increasing this, shifting to the right. So this would go to the right. So then that's 2, 2, 4, 5, and 8. So that's 15. For number 9, right, this is kind of like integrated rate laws. So we know that this is a first order reaction. So we know that ln of a t is equal to negative kt plus the ln of a 0. So we're looking for it to decrease to 14.6% of its initial value. So you can use this integrated rate law and the half-life. We know that T1/2 is equal to ln of 2 over k. So in order to find k for this reaction, because we're not given that, we can plug in 14 hours into ln of 2 over k, and we can solve for k this way. So we get k is equal to 0.0495 1 over hours. And remember, this is a first order reaction. So your k value is always going to have units of 1 over time, right? Whether that's seconds, hours, minutes, days, weeks, months. It does not matter as long as you have a 1 over time component. Once you have that k, you'll plug this into 0.146. Because we're looking for 14.6% of its initial value, right? So that's the value we're ending with. You can either use the 14.6 directly as is, or you can change it to a decimal like I did, or you can come up with the number 20 and get 14.6% of that's original value. Whatever is easiest to you, as long as it has the ratio of 100 to 14.6%. Then you'll use your k you just solved for. You're looking for t, and then you have the ln of 1. And then you can get t is about, I think, 39 hours, if I remember correctly. The other thing to notice here is that if you go from 100 to 50 to 25 to 12.5, you're about here in remaining material. So you had to go through 1, 2, almost 3 half-lives. So if you do 14 times 3, that gets you to 42 hours. You're close to 42 hours, and so the closest thing to 42 hours is 39. So that's a good way to check your answer. So on your formula sheet, you are not given, where to go? Right, you're only given these integrated rate laws. So you do need to know the half-life formulas if you want to use them directly. However, for anything T1/2, you're just looking at 100% versus 50%. So if you want to find the k value using the integrated rate laws that's not the half-life formula, then you're just gonna plug in 0.5 over 1 for all of these. And then T becomes T1/2 because you're solving for the half-life of that material. Same thing here, it would be 1 over 0.5 minus 1 over 1 is equal to K times T1/2. Oops, that's the wrong thing. These are your half-lives. And then, right, this one is 0.5 minus 1 equal to K times T1. Right, so you can still solve for T1/2, it's just using the integrated rate law and not the half-life. I think I have time for one more question. So for number 6, right, you're given 10 moles, 25 moles in a 10-liter container. So so when you look at this, right, all of your ice tables and all of your equilibriums have to be in molarity. So if you're given moles in a liter, make sure you convert those to molarity first. So if you're looking at an ice table, you have 2 N2O gas plus N2H4 going to 3N2 and 2H2O. If you're starting with 0.1 moles of N2O and 0.25 moles of N2H4 in a 10-liter container, you need to take your moles and divide by 10 first. So you have 0.010 moles or molar here, and you have 0.025 molar here. And then they're saying that, right, then you have 0, 0. So if you look at your change, it'll be minus 2x, x, 3x, and plus 2x. And then at equilibrium, we have 0.048 moles of N2O2, which means not at equilibrium, you don't have 0.048 moles, you have 0.0048 molar in your solution. So if you wanted to find how many moles of N2 are present, we know N2 is 3x. We have everything right here in our ice table, so we can set this up where we have 0.010 minus 2x is equal to 0.0048. So we end up with 0.0052 equal to 2x, and x will equal 0.0026. So then you'll take this, plug it into here, and you get 7.28. Right, you get 3 times x, which is 3 times 0.0026, which is 0.0078 molar. So to get to moles, then you multiply by 10. So you get 0.078, which is B. Sorry, that was kind of fast. If you forget to do this one without converting to liters or converting to molars, it should come out to the same answer. But in a case where they ask you for something slightly different, do make sure that you're working in molarity for your ice tables. Okay, any other quick questions that I can answer before we wrap up for today? If you have any additional questions, please feel free to email me. I'm happy to answer them in the meantime. Good luck. Make sure you set multiple alarms and look for me tomorrow and say thank you. And thank you for being a great class and a great semester. And it's been a privilege to be your IA, and I'll be here a little bit longer. So if you need anything in the meantime or next year at all, feel free to email me and I'm happy to help you again.
May I ask one question regarding grading, like not concept?
Yeah,
Like,
sure. Yep.
so when I was looking at the grade book, I noticed that our final grade is weighted at like 110%. I just want to make sure, is that like something extra, or do you know what that extra
That might
10%
just be the
is?
setting that's on there right now. If you look at your syllabus, then that will show you what the weight of the final is. I think it's like 40%.
40%?
Yeah, I think.
Okay. All right. I just want to make sure.
Yeah.
Thank you.
Yep. And then for 16 real quick, right, how I solved this was you look at the periodic table. You look at the periodic table for the mass. And then I used this the first time, but I mean, this is how you should do it. Right? If you use it this way, then you get B. If you fuddle with the numbers a little bit, I think if you use 63 times X and 65 times 1 minus X, then that gets you this guy. But if as long as you get B or C as the answer, then that. Sorry, I have no idea. I literally don't know anything. Okay, so then if you just do 63 equal to 62.9296 times X. Then you get this guy. Sorry for the freak out on the final exam. That might be the other class I have.
So on the actual exam, if we do work it out, we should get the same number.
On the actual exam, I would look at your periodic table. I would look at your periodic table.
Okay.
Yeah. Okay, any other questions? Cool. Yep, normal classroom, 10:30. Only 25% of your grade.
Wait, can you go over one more question on the practice final?
If it's quick.
If it's quick, okay. Hopefully it was question. Let me check which one it was. Sorry, I have it out. It was
Yeah, I don't think.
wait, I'm sorry. I have it. Oh, 33.
Yeah,
No.
nope, you don't have to do that.
Oh, can we go over 33?
I don't think we did that topic. You didn't talk about KSP.
Oh, okay. I just want to make sure because I saw that and I thought,
Yeah, I don't think we got to KSP.
all right, I got it. Thank you.
Yep. Cool. Alrighty, I'll end that there. Thanks, everyone. Have a great rest of your day. See you tomorrow.
Thank you.
Get some sleep, eat a breakfast, all the fun stuff there. It's been a pleasure.